Okay, you're recording.
Okay, ladies and gentlemen, this is the last portion of the course, on the handout on heat transfer. I think we left off in the last section of this. Most of this we sort of went over with. Again, a lot of this information is still in Gupta and also in Yodel's books. Anyway, Yodel books. Let's finish it up. I think we were way down in here, if I'm not mistaken. Steps to commission, drainage, procedures, tube rupture. And continuing on, we talked about different codes. I think we left off right about in here, if I'm not mistaken. So this time we got, this is slide 31. We got 56 slides total. So we got, 25 slides to go through. Most frequent causes of most frequent failures, obviously, fouling, erosion, and corrosion. And other modes might be fatigue wear, or wear, mechanical wear, or fracture by stresses. Fouling is accumulation of solids on walls and the inner surface. The nature of fouling is process specific and process dependent, and following guidelines are. Basically, you think about in high school, you took a chemistry course, you took a physics course, and you took a biology course. Well, those are the three ways things foul. You can have a chemical phenomena, you can have a physical phenomena, or you can have a biological phenomena. Chemical phenomena, you could potentially have things fouling because of polymerization, coking, corrosion would be in there. Line crystallization, possibly. Physical would be sedimentation, settling. Crystallization would be, I guess, could potentially be either considered physical or chemical. Then you have microbial growth, like bacteria, slime, algae, that sort of thing can obviously foul something. Anyway, crystallization can easily occur. Biological materials cause scale formation. If you look at a boat, oftentimes they have to pull the boat to clean off the hull. The buildup of the material on the hull, they have to scrape it off. Be sort of like growth of biological animals of sorts, oysters or whatever. It causes corrosion, basically. Biological materials can cause corrosion from their waste products. Some of these biological entities can produce hydrogen sulfide, which is very corrosive. Hydrogen sulfide is very, very dangerous. It smells like rotten eggs. Basically, rotten eggs is. Solubility of some salts decrease with increasing temperature. So here you have a salt that's dissolved in a liquid, and you go ahead and heat it up. It then crystallizes out, reverse solubility salts. Negative effects of fouling: localized corrosion, throughput, reduced heat transfer, increased pressure drop. And typically you write this, you have 1 over UD. U is the overall heat transfer coefficient, dirty. And then you have 1 over UC, clean. Okay, when you clean your heat exchanger, you have a measurement of that. And over time, as it gets dirtier and dirtier and the fouling accumulates, you can monitor this UD over time. So you have one fouling factor outside the tubes, perhaps, and you have one fouling factor inside the tubes. Fouling factors have units of heat transfer resistance. So here you have effective fouling on heat transfer surface requirements, right? Anyway, we'll let you rotate that. I'm giving up on rotating here. This is perhaps worthy of rotation, so we'll rotate this. Fouling resistance. Typically, you can have stuff that fouls to an asymptotic, or you can have fouling continuing. Your radiator probably fouls to a certain level, and it no longer fouls with time, it fouls. This one is the one that's the problem, continuously builds up. A chap of mine that worked for DuPont down in Goldsboro, North Carolina, he had a pipe that would foul shut in a period of a month. It would start out like a 2-inch pipe, and at the end of the month it would have been fouled shut, basically 1/4 inch in diameter flow in there. What's interesting is this item called the induction period. Now, this is a very mysterious concept, but sometimes it takes a while for nature to get its act together. It doesn't quite know what it wants to do, and then it suddenly takes off. So lots of things in nature have a time of which it takes it to get going, so to speak. Chemical reactions are notorious for this. You add a monomer initiator to a monomer, it'll sit there for a while, and then it will polymerize. Let's see what we got over here. Euclid required percent increase in area versus fouling resistance. I've never really paid much attention to this graph. Anyway. So I got a sneaking suspicion that we probably are not going to be successful with this. Apparently we're not. So we're going to go, what did we do last time? We basically started anew with fresh. So I think we were down around page 38. Actually 31. Let's go back here. This is where we were. All factors influencing fouling: formed by reaction in chemical dependent environment. Fouling material formed by corrosion, which depends upon the presence of dissolved oxygen or dissolved air or CO2. Fouling materials, impurities or dissolved materials that leaves the solution. Environment in which deposits can occur: low velocity, laminar flow, stagnant regions, high temperatures, large amounts of settled material. Nature of the surface: some materials and surface textures are important. We'll do it that way. Difficult to adhere to, perhaps. Surface treatment, like you have a no-stick cooking pan. Okay, it has a Teflon coating or some coating in there that prevents sticking. That would be great if it didn't wear away, or basically surfaces could be hindered fouling. The nature of the surface charge could actually be important. Surfaces carry charge, period. So it could be a plus charge, could be a minus charge, or a net minus or a net positive, right? Fouling in laminar flow is higher than in turbulent flow. Turbulent flow has more or less a scrubbing action to it. Lots of surface renewal, right? And fouling factors for laminar flow can be twice that in turbulent flow. Process is often naturally foul. Evaporation leaves behind crystals. Condensing of polymers is notorious. De-waxing operations in crude oil. The waxing itself is a fouling material. Process changes: increased velocity, increased surface scrubbing, decreased wall temperature. Fouling due to chemical reaction. If you decrease wall temperature with reverse soluble salts, you might be able to Remember, at higher temperatures, these things crystallize out. At lower temperatures, they dissolve. So, increased wall temperature, the fluid next is less viscous, more mobile, less likely to plug like waxes. So you have increasing velocity, increasing surface carbureting. These two, obviously decreasing wall temperature or increasing wall temperature, right? Two different directions will decrease fouling depending upon the processing conditions. Change materials. Use copper, stainless to prevent microbial fouling, decrease oxygen or CO2, to decrease corrosion, eliminate stagnation regions. Do proper design. Use spiral heat exchangers if you have suspended solids. There are such things as anti-fouliants and dispersants. And obviously, periodically cleaning your surface is a great idea. You brush your teeth every morning, and primarily, well, maybe not every morning. Maybe you're brushing your teeth morning, noon, and night. Obviously, that's going to keep your teeth from fouling, so to speak. Reduce the amount of material that causes fouling. Do blowdowns. Now, you blow your nose. That's basically a blowdown of your sinuses, right? You want to blow out any of the settled solids in there. Talk about Tatterson's water heater here. That's what one kid wrote about one time. I had my water heater was acting up a lot. I don't know if you know anything about water heater, but the idea of the life of about 15, 20 years. Anyway, this one particular water heater is 20 years or so. So my house was 20 years old, or 17, 18 years old. And I was out to dinner with my buddy who works in the housing industry, and he says, you know, water heaters are really strange. He says, you got a 20-year water heater, it's acting up. You do a blowdown, blow out all the solids in there, then it would have another 20 years of life in it. So here I did. I had my water heater acting up, called in the plumbers. They put in a new valve for exiting, right? The water heater, in case it gets over pressurized, apparently has this valve that opens up. Anyway, I did a blowdown on my water heater. That was 2 or 3 years ago, and I haven't had to replace my water heater, i.e. about 18 years in, water heater was acting up. Could have had it been replaced. Or I followed the directions of my buddy, did a blowdown, got rid of all the debris in the water heater, and now it's working fine. Didn't have to replace it. And you do a blowdown, you got a lot of dirt, sand, corrosion products, maybe organics in there, slime, algae, maybe aluminum, all kinds of stuff in there, all kinds of salts in there. And just like your nose, you're blowing down the snot in your sinuses, and then you do the same thing with your equipment. You, of course, need to design for cleaning now there. Needs access to fouling surface. Places in the foul fluid, tube side, great. So I want you to go on the YouTube, and I want you to type in shell and tube heat exchangers, cleaning of shell and tube heat exchangers, and I want you to watch them do some cleaning. Use straight tubes. U-tubes are difficult to clean. High fouling materials, use the larger diameter tubes, using thicker tubes, right? Channel covers are easy to access tubes. Horizontal installation is easier to clean, no scaffolds. Cleaning the shell, you got to use, what do we have here? Where was I? Designed for cleaning. Have channel covers for easy access to tubes. Horizontal installation, no scaffolding. Cleaning is required for shell side. Use large square pitch or large triangle with pitches with cleaning lanes. Notch the baffles at the bottom to allow drainage. Now that's why you notch baffles at the bottom, to allow for drainage, right? Your bathtub has a certain tilt to it, doesn't it? It doesn't tilt away up, excuse me, it doesn't tilt down away from the drain. It tilts up away from the drain, right? So the water well or bathtub fluid will drain, right? Same thing with heat exchangers. Heat exchangers need notched baffles that allow drainage through the bottom, right? And then you need to put a slight angle on the heat exchanger, much like your bathtub has a slight angle for drainage, right? Now then, there you go. You know twice as much as those people from a certain company came in here, and they were really proud they were going to help us out with design. I love it. I love it. They were young kids, about 35, you know, engineers. They got 10 years experience. They knew everything there was to know. And they kept on telling me, you got to notch your baffles. Got to notch your baffles. They were here for a couple of days, and they must have said that to me about 4 times, 5 times. They were trying to show their knowledge. I was right impressed myself. Notch your baffles. What can I say? Young people, they're still learning. Anyway, by the way, 35 years old is still young, right? 40. I knew everything back then. Myself, personally, I knew everything back then. Now I don't trust a damn thing I know. Place heat exchanger slight angle, allow for drainage, but not a situational angle to prevent excessive of a volume of the shell, access to prevent volume of the shell. Drainage ports, blow down vents, good idea, blow down vents. Back flushing heat exchanger, there you go. Back flushing. How's a toilet bowl plunger work? You know how it works? Anyway, just giving you a little test there. Fouling treatments, overall, reduce the overall extent. Treatment is necessary until next scheduled maintenance. Cleaning can be a part of this. And know the nature of your fouling. Try a fouling analysis. Don't use standard fouling factors in treatment unless you don't have any other sources. If you have a badly fouled exchanger, find out what the fouling material is, and you do want to do a chemical analysis. Again, I'm drawing an analogy between fouling and heat exchanger and kidney stones. Kidney stones contain oxalate, so you don't incorporate any oxalate in your diet. Cleaning methods, all sorts of cleaning methods, circulating and flushing with cleaning solutions, back flushing, basically biological and chemical. You use hydrochloric acid, sulfuric, but I don't know, sulfuric acid might not go well with stainless steel. I said that earlier. You might want to check on that. Nitric, biocides, chlorine and stainless steel. Yeah, that's the one that don't mix, chlorine and stainless steel. Got some other biocides. Rotting inside tubes. You know what rotting is? Hydroblasting, sandblasting, wire brushes, scrapers, reamers, long cutters, polish after cleaning. Oh Lord, sponge balls. Now this is not, I think this is pretty ridiculous. But don't let me stand in front of the British. Thermal shock's pretty cool. You have a device, the scale built up, so you hit it with a lot of cold water or a lot of hot steam, expand the tubes, crack the crust. You can also have tubes that are spiraled, okay, like truck springs, and you can actually rotate them a bit. You hold one end stationary, you rotate the other end. That way you can remove any scale buildup just by the twisting on the spring. Kind of a good way of anything that's going to be excessive buildup of fouling material. Perhaps you have a heat exchanger inside a thermal pond that's evaporating water to catch the salt, to get salt. In such a manner, if you have a heat exchanger to be adding the heat instead of the solar pond, you would want to have spiral tubes that you can flex to get rid of the salt deposits on the tubes. Now this rubber ball thing, I guess I put this in here because this is about the craziest thing I ever seen in here. So they run rubber balls through the heat exchanger, and obviously then they have to have a collector for the sponge balls so they can retake and incorporate it back. I'll tell you, these guys, I don't know if this thing works, right? But they claim you send a sponge ball down the tube every 3 or 4 minutes, then obviously the tube wouldn't foul as much. And here you have a picture of the fouling deposits. Inner tubes are random, cleans, cut, and recycle. Tubes cleaned every 5 minutes. Which to use depends upon the type. Fouling, best bet, see which one works. Okay, you got these guys trying to sell you a sponge ball unit, right? So you ask to visit a site that uses this thing. If they've sold it before, somebody bought it and they're incorporating it. Obviously, you want to go talk to them, right? Talk to what their experiences is of using this stuff. Okay, got it. Society is, or how can I say this? Companies are very close-knit. They don't like to talk about things very much, right? So that's often the case. However, such things as maintenance or preventive maintenance, they tend to get together and form maintenance meetings. What do you do about that problem? What do you do about this problem? And their maintenance people and operators sit around talking about general problems that they all face, which doesn't involve business aspects like making money. So they have a free exchange of information. So it's not uncommon for you to go out and get information from some other company who's using the same piece of equipment but producing a different product. Chemical, mechanical are combined. Access to surfaces to be cleaned. The nature and extent of fouling and construction should be designed with cleaning in mind. Cleaning in mind. Shell side often chemical cleaned, avoids the removal of tube bundle. Don't leave the cleaning solution in the exchanger. That's probably a good idea. Mechanical cleaning is difficult. Care must be taken. Don't damage the tubes, tube sheet, joints, protective coatings. I don't know exactly what that means, protective coatings, because if there are some, they're probably gone. You buy a Teflon lined cooking pan. Teflon's only going to last so many, and before it just gets cut away. Requires dismantling the heat exchanger, removing the bundle. That means tube bundle. That means long downtime. And fixed head exchangers, tube bundle can't be removed, so mechanical cleaning can be more difficult. Again, I mentioned this. U-tubes are difficult to clean. Water treatment, important to remove materials from water to prevent fouling. Use soft water without minerals. Calcium and magnesium are scale producing, not good for boilers or coolers. Important in all water systems, closed, open, straight through. With an open system with recycle, recycle is often the first thing chemical engineers do. When it doesn't work, you do a recycle. So as a result, you don't know exactly what the system would do without recycle. Okay, so that might be interesting. Reduce water hardness. You might want to add lime, add a mineral mineral acid like sulfuric acid. Inhibit crystal growth by organic phosphates, monomers, and polyphosphates. Filter, remove solids. Reduce microbe by using biocides. Corrosion prevention methods are given below. Well, you got boiler water composition. This is covered by American Boiler Manufacturers Association. High temperatures, some dissolved compounds become insoluble. That's true. Reverse soluble salt's a concept. You can let a human drink it, but don't give it to a boiler. All sorts of ways to treat water. Screening, coagulation, flocculation, precipitation, distillation, evaporation, reverse osmosis, ion exchange, deaeration, chemical and biocide additions, corrosion inhibitors. Excellent article on filing. Now, let me explain something to you. Maybe you didn't catch that, but let me explain it to you here. Go back to where I was. Right. That's 1991. Nothing has changed. Oh, we got new life. We have a new era, right? 2017. 1991, it filed. 2017 files the same way. Right. This business about what's new, you won't find much of what's new. It's often the repeat of what's already known. Erosion, that's kind of interesting. Loss of material due to high velocity. Occurs at inlet to tubes and also entrances to the shell. Occurs when two-phase flow occurs, right? Cavitation, special type of erosion due to the collapse of superheated bubbles. Superheated bubbles are unstable, and when they collapse in a manner that you would not anticipate. They can generate very high pressure jets, 50,000 psi, which can eat through metal, so causing impeller blades to fall off. Impingement plates are useful in preventing erosion. Baffles, basically. A well-placed baffle, great stuff there, well-placed baffle. Velocity of magnitude, you can expect erosion to start occurring for liquids up to 60 feet a second. Second or third phase causes erosion. Again, the idea of perhaps filtering your streams, or you might try wear-resistant materials, right? Reduce the erosion materials by filtering, have a gradual changing flow paths. Impingement plates, avoid sudden pressure drops. I mentioned my other courses. Met a young lady who had an engineering job in France. She had a pressure drop of 300 psi across this one valve. And she was wondering why the valve disappeared on her after a month. Well, she had such a huge pressure drop. The velocities were so huge going through that valve. Pressure drop means velocity increase. That just drilled her valve away, basically. You want to avoid cavitation, avoid erosion, corrosion, rotate two bundles. Erosion is going to be uneven. Corrosion, everything corrodes all the time. When I was growing up, I got the impression that plastics don't corrode. Well, metal will corrode. Plastics don't. However, that's not necessarily true. If you look at how your lawn furniture corrodes, it could generate a white powder on the surface. And that's, you wipe off the white powder and the next year it's there again, right? So 8 forms of corrosion, there they are, fantastic, 8 forms of corrosion. Let's do the rotation on this where we pay the price here. Uniform corrosion, galvanic, crevice, pitting, intergranular, selective leaching, erosion, corrosion, and stress. Acceleration corrosion due to relative movement between fluid and the metal. Seawater erosion of condenser tubes. Corrosion of pump impellers. All right. Here we go. Chlorine pitting of stainless steel. Pitting of aluminum brass condenser tubes. These are examples. So don't use chlorine and stainless steel together. What else don't you want to use? dezinkification of brasses. That's kind of interesting. Brass is a mixture of copper and zinc, I think, right? Cracking of stainless steel in chlorine environment. There you go. Carbon steel in contact with stainless steel tubes. There you go. You set up essentially a battery that way. So 8 forms of corrosion. You can spend your life on corrosion, right? Wow, look at that name down there. That's an extraordinary name. 1979. I got news for you. People knew 8 forms of corrosion before 1979. How about 1940s? How about 1920s? Anyway, fantastic book on corrosion. You might try Fontaine. Guy named Fontaine or Fontaine. It was excellent chap on corrosion. Okay, let's go back here and start anew. Prevent the rotation problem we have. I think we were around about 40. Go back up a few here. Oh, we're past that, right? 41. We're getting near here. We were talking about. Oh, yeah. Look at all this good stuff. You can give it to a boiler, but don't give it. Okay, I think we're about right in here, if I'm not mistaken. 8 forms of corrosion. Factors affecting corrosion, material combinations. Anything that's dissimilar. Metals. Wow. Composition of compounds, internal structure of compounds, mechanical state. I mean, if the metal's cracked, thermomechanical stress histories, environmental, operational, corroding reactors, availability of corroding species, pH, temperature, corrosion cells, flow velocity, stagnant regions. Nature of surface and design shapes, formation of deposits, formation of protective layers, sharp edges, bends, surface roughness are all considerations to be accounted for. Cost of corrosion, lots. Replacement cost, cost of labor, cost of preventive maintenance, and cost of shutdown. Tube sheet corrosion, right? Galvanic corrosion, you have 2 dissimilar metals. Stress corrosion in the tube sheet, crevice corrosion, uniform pitting, uniform corrosion. Force permits corrosion of cells to form. Streams in acid or alkalines, not good. Alkalines are basically bases. Steam generators, ways to prevent corrosion. Well, you want to prevent this reaction right here. Corrosion is allowing the reaction metal to a metal plus and an electron to occur. The whole idea is to prevent this from happening. The electron is then used with O2 to form hydroxide ions, and that's that's an acid, by the way. So, objectives to eliminate this reaction. Right. Removing dissolved oxygen helps. Maintaining a slightly basic solution. Basic solution will prevent the ions from forming. Particles to cleaning. Method 2, cleaning. Okay, method 3, particles tend to attract the surfaces, keep surfaces clean, limit solids blow down. Sacrificial corrosion, this is what they do along the beach all the time. You could go to the beach. You have a lot of chlorine floating around in the beach. Lots of things corroding away, aluminum corroding away. You can make a lot of money setting up an anti-corrosion company at the beach. Steam condensation. Yeah, that's kind of interesting. Steam is very corrosive if it has dissolved oxygen in it. or if it has CO2. Okay. Place on tube side, designed for continuous drainage. Condensate will fill the tubes if not drained, block the area only partially drained. Fuels have sulfur in it. And obviously the sulfur dioxide, which could form because of oxygen present, you make sulfuric acid. All right. Let's see. High corrosion rates occur at high heat flux. All materials corrode. Assume all materials corrode. Rates important. Various books look these up. Typical corrosion tests, very important. You can run your corrosion tests, put in an environment of interest, and see how much weight loss you have per time. Basically, you take a chunk of metal, put it in your fluid, see how it changes with time. Run it hot, run it cold. Corrosive environments are possible. You want to avoid them. Cracks, sharp ends, edges, stagnant vapor pockets, excessive particle settling, contact to similar metals, that ain't good. Excessive mechanical stresses, hot spots, high velocity impingements, air pockets. To-do list, designed for easy draining, designed for tube and baffle replacements. Replacing a tube's tough. You just plug the thing. Provide preventive coatings and linings, weld instead of riveting. That's interesting. Weld forms a solid barrier. Riveting, it lets two planes come together, which are still exposed to the environment. Provide high flow rate through the equipment, prevent settling. Designed so surface to volume ratios are small. That tends to be difficult to accomplish. Anyway, methods for minimizing corrosion. Right, and I think we're coming down to the very end. Vibrations, a little bit of vibrations. I think I'm at the end here. Just to throw some things out. Vibrations can be flow-induced. Mostly flow-induced. Tubes vibrating quickly, increases in amplitude, natural frequency, causes a resonance, can cause the tubes to come apart. High flow rates being used, large exchangers are being built, no data on reliability of exchangers. No accurate method to predict vibration behavior, may cause tube rupture. Resonance phenomena can occur. Anyway, I've run out. This is page 56 and 56. That means I'm done. I hope it was worthwhile for you. There's again, this is abbreviated stuff. From Gupta's book in particular. Anyway, I hope you enjoy this material. Hope you learned something. And I'll stop there. You have a good day. I'm done. Thank you.
You're welcome.